Hello, Honors Chemistry, and welcome to the last chunk of Chapter 9, where we are going to talk about the things we can predict based on knowing electron configurations, right? So basically, this is why it's important at the atomic level to understand electron configurations. First, we're going to start with a summary, right, of the quantum mechanical model, just to sort of refresh our memories and make sure that everybody is on the same page about what we've been talking about. So first we have our shells, right? And our shells dictate broadly how far we are from the nucleus, right? Where n equals 1 is the shell closest to the nucleus, and each subsequent shell is a little bit further and a little bit further, right? For those of you that are very visual, you can sort of think of it like nesting dolls, right? There's also that link on PowerSchool, right, that takes you to a little game that allows you to sort of build the shells and subshells together, which also might help if visualizing it might help you to grasp it better, right? So anyway, we have our shells. Each shell, based on the shell number, is allowed a certain number of subshells, right? Wherein the subshell, right, is just the predicted three-dimensional region where we might find an electron, right? So the S subshell has a shape. The P subshell has a shape, D, F, G, H, I, etc., right? Every subshell has its own shape, which again represents the three-dimensional region where we might find an electron, right? And then building on that, right, remember that each of these subshells come in sets, right? In that a set of s orbitals, well, s orbitals are always just one, right? Those are s orbitals. P orbitals always come in a set of 3, right? D orbitals come in a set of 5, F orbitals come in a set of 7, right? So forth and so on, right? And each orbital is capable of holding up to 2 electrons, right? So shell, subshell, orbitals, electrons, okay? Now, in the previous section, we talked about how there's that little diagonal rule chart that allows us to sort of know, right, how to fill electrons from the lowest energy up, right? Which is kind of like you have to memorize it, and it seems, weird and confusing, but it turns out, right, that part of the reason, part of the confirmation for the quantum mechanical model comes from the periodic table itself, right? In that when we look at how the elements are arranged, it falls exactly in line with what we know about the quantum mechanical model, right? So for example, if we take a look here, right, we see that hydrogen is 1s1, right, which we've already talked about. Helium is 1s2. Oh, look, lithium is 2s1, 2s2. These are 2s and 2p, etc., right? 3s1. And if we look carefully, we'll see, oh, well, look at that. The period number corresponds to the valence shell of every atom, right? So, for example, if we were to look at gold, right, its valence, or its outermost shell, is 6, right? And it happens to be in period 6, right? Or if we were to look at, say, radium, right? Highest shell is 7, it's in period 7, right? If we were to look at selenium, oh, we've got some 4s here for our shell number, it's in period 4. So again, the period tells us what the outermost shell is for any particular element, right? And now, if we want to layer on some more information, right, let's get a different color. If we take a look, right, we'll see that these group 1A and group 2A, right, are always filling their S subshell, right? So we have S1, 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 S2, 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 right? This is known as the S block, where all of those elements are filling their S subshell, right? The S subshell that corresponds to their period, right? If we look over here at this pink section, right, this is known as our P block, like it says up top, right? And that P block is where we're filling our P's. And look, oh my gosh, 1, 2, 3, 4, 5, 6. That's exactly how many electrons go into the P subshell, right? And then when we put our S block and P block together, that makes 8, which again goes back to making our valence for every one of our elements, right? Okay, so then, and then we have the orange as our D block and the purple is our F block. And again, if we count those across, right, we'll see that, oh my gosh, they happen to fit just right with the 10 and the 14, okay? So then the beauty of that is that, and then the number of valence electrons, right? So if we look here, for example, 7A has 7 valence electrons, which we can count by 2s2, 2p5, total of 7, right? S2, P5, total of 7. And again, going back to the fact that all the elements in a group exhibit similar behavior, well, that's because their valences look the same. And again, going back to chapter 4, those valence electrons are the ones that are available to do the sharing or the giving and taking to form chemical bonds, right? So if they have the same valence, that means they'll behave the same, right? They have the same number of electrons to give, take, or share, right? So again, this just sort of emphasizes all the things we've been talking about, right? Using this, though, we can go ahead and we can use this to go ahead and write some electron configurations really easily, right? So again, we don't have to memorize all that stuff. We just know them now. So for example, let's say we wanted to write the electron configuration for phosphorus, right? So we would just, kind of like a board game, we would just cross out every block on the way to phosphorus, right? So we've already passed these, right? So 1s2. We've passed this, that's 2s2. We've passed this, that's 2p6. 3s2, 3p3, right? And that is phosphorus based on phosphorus's location, yes? Or for example, if we wanted to do something different like manganese, right? Same principle, right? We've passed that part up here, right? So 1s2, right? 2s2, 2p6, 3s2, 3p6, 4s2, and here is where we do have to memorize a little bit, right? That our D's are back 1, right? So 3D, 1, 2, 3, 4, 5, 3D5, right? And so again, right, the D's are going to be back 1 shell, the F's are going to be back 2 shells, okay? So when we're in period 4, these are going to be 3D. When we're in period 5, these are going to be 4D. Yes, does that make sense, right? When we get down here to 6, right, this will be 5D and 4F, right? Because again, D's are back 1, F's are back 2. And really, so then the electron configuration for every element is already written on the periodic table, okay? Hopefully you'll practice and that will sink into you. And if not, you can use the diagonal rule and that will be fine also. All right, now, again, periodic table tells us information, right? The arrangement of electrons gives us information. So here, if we take a look, this is the chart from your book about the relative sizes of some main group elements. We'll see that the general trend is that as we go down a group, the atoms tend to increase, right? The size of the atom. And when we say size, another word for that is radius, where radius is approximately from the nucleus to the outermost edge of the atom, right? Different books will define it differently, right? It is most often when it's bonded to an atom of the same thing, right? The distance, the halfway distance in between them, right? But anyway, as we go down a group, the atom size increases, which makes sense because we just said in this previous chart, right, that as we go down a group, we add shells, right? Which makes sense. If we are adding a shell, the atom is necessarily larger. Yes, I feel like that makes sense, right? As we go across a period, and when we say across, we always mean left to right. As we go across a period, we'll see that the atoms tend to, right, they tend to decrease in size. As we go across a period, the atoms tend to decrease in size, right? And this has to do with an increased force of attraction between, specifically, the valence electrons and the nucleus, right? And so one of the ways we can think about this, right, is that we are adding electrons to the same shell, right? Because that's what we just said over here, right? That as we go across period 2, for example, right, we are adding electrons to the second shell, right? So again, we're adding electrons to the same shell while also increasing the number of protons in the nucleus. And so what that's kind of like doing is it just kind of means that we're increasing the attraction, right? We're increasing the amount of opposite charge that is in relative proximity to one another, and that force of attraction increases, and my atom gets a little bit smaller, right? And the neat thing about atomic size is it explains the other two trends, right? Because if we think about this, ionization energy, right? So what is ionization energy? Ionization energy is the amount of energy required, positive, right? Amount of energy required to remove an electron from an atom, okay? Now, it says that as we go down a group, ionization energy decreases, right? Which means that as we go down a group, it costs less to remove an electron. As we go down a group, it costs less to remove an electron. That's because there is a decreased attraction, okay, between the valence and the nucleus, right? Because that's what all of this is driven by, right? Nucleus, right? Is that those valence electrons are attracted to the nucleus. More attraction, harder to remove. Less attraction, easier to remove, right? As we go down a group, if the valence is further and further from the nucleus, there's less and less attraction, right? Again, as the valence is further from the nucleus, there is less attraction, which means it's easier to remove, right? Opposite, if we're thinking about across a period, because as we go across a period, we already said that as we add electrons to the same shell, that force of attraction increases between the valence and the nucleus, which means it's harder, right? It's going to cost more energy to remove an electron. Yes? All right. Next up, metallic character. What does that mean? Right, that is the tendency to lose electrons, the ease with which an element can lose electrons or give away its electrons, right? So it says metallic character increases as we go down a group. Again, makes sense, right? If the atomic size gets larger, that valence is further from the nucleus, less attraction, those electrons are lost more easily. That element is more metallic, right? And here, metallic character decreases, right? Meaning it is less and less metallic as we go across the periodic table, less and less likely to lose electrons, right? Which again, right, goes back to attraction. As we go across the period, we're adding electrons to the same shell. They are more attracted to the nucleus, right? And the stronger that attraction is, the harder it is to lose those electrons, right? Which is why, oh my gosh, nonmetals are located over here, right? I mean, I could have drawn that better. They're located over here, right? Those are our nonmetals, right? So yeah, does that make sense? So in terms of identifying a most metallic element, right? Ding, 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 right? Most metallic element most readily loses its electrons. All right, so again, right? We started with light because light gives us insight into what the inside of an atom looks like, right? Once we know what the inside of an atom looks like and the distribution of its electrons, right? We can make charts like these, right? That tell us how we can predict how something's going to behave, right? Which matters because in chapter 10, we're now going to start talking about what happens when we take an atom and try to bond it to other atoms, right? What new properties come about because of that, right? All right. Thank you for listening. Be good, and I will see you soon for more practice. All right. Be good. Bye.